Last time we looked at the procedure for Gram-Schmidt orthonormalization, which was utilized to obtain a orthonormal basis set. Today we are going to discuss some of the related results which are useful. It's going to be a short lecture. So to begin with, I would just recall the three orthonormal basis vectors which were obtained in the previous class. They are respectively phi1, which is 1 over root 3, 1, 1, 1, phi2, which is 1 over root 6, 1, 1 minus 2, and phi3, which is 1 over root 2, 1 minus 1, 0. So what we do now is essentially construct a set of outer products. So that means taking a product of ket of phi1 with bra of phi1, and similarly repeat the process for phi2 and phi3 respectively. So this way, when we obtain this outer product of phi1 with phi1, which is this, phi2 with phi2 and phi3 with phi3, and add them together, that essentially leads to this identity matrix. And that brings us to an interesting result, which is known as completeness theorem. So in general, for any orthonormal basis set, the sum of phi k is going to be an identity matrix. So this extends to the scenario where phi k could be an infinite dimensional ket vector. So the next thing that is relevant here is to understand this transformation between basis sets. So last time we saw that these basis sets need not be unique. So you can get a set of basis sets, each of which could be used to span the linear vector space. Okay, so let's assume that we have a particular ket vector psi, and we are expanding it in terms of basis sets which are phi k and rho k respectively. So when we expand psi in terms of phi k, the corresponding coefficients are ak's, and similarly when we expand psi in terms of the rho k basis, the corresponding coefficients are bk. And the question I'm asking is, how are AKs and BKs related, if at all there is a relationship? Or is there more universal results which these AKs and BKs are going to satisfy? So before that, we would just like to see how do we transform from a basis set phi k to rho k and vice versa, and what would be the connecting coefficients, and what would be the relationship between AKs and BKs. So for doing that, suppose we are looking at psi expanded in terms of the basis set phi k. What we do essentially is introduce a complete set of states of rho k basis. So that means in this particular result, we are primarily adding this part, which is ket of rho j, bra of rho j, which is the outer product of these basis vectors, and summed over all j. So because this is identity, so it does not really change the result. However, with a little rearrangement, we see that we are able to pick out this inner products which are between the rho j and phi k basis sets, and the result now is an expansion in terms of the rho j basis set. So that brings us to a connection between BJs and AKs. So therefore, this BJ is going to be sum over K, AK of inner product of rho j with phi k. So that's a useful relationship. And the converse relationship is also possible. In that case, to start with, we are going to expand psi in terms of the rho k basis set and then introduce the complete set of state, which is phi j phi j. The inner product of phi j with rho k appears in the expression on a little rearrangement, and therefore we are going to have this written in terms of aj phi j summed over all j. That brings us the relationship between aj's and bk's. So that's how one can therefore see that one can transform a given eigenvector from a given basis set to another basis set. This is particularly useful in physics when we are doing quantum mechanics, where one has to make transformation between the real space and momentum space quite often. The next result is about this basis independence of the inner product. So let us consider vectors small a ket and capital A ket and basis sets phi k and rho k as before. And let's write down AK, write down the A ket in terms of the phi k basis and the rho k basis, where the corresponding coefficients in the expansion are ck's and dk's. These are small letters c's and small letter d's. Similarly, capital A ket could be written in terms of phi k and rho k basis sets. And in this case, the coefficients we denote by the capital CK and capital DK respectively. So using orthonormality of the basis set, we know that inner product of phi k and phi j is the Kronecker delta ij. And similarly, rho k, rho j is going to be delta ij, which essentially means that if phi k are identical, then this inner product is 1. And if they are different, like they belong to different labels k's or j's, in that scenario, the inner product is 0. So that brings us to an interesting result where when we find the inner product between the small a and capital A ket vectors, that is equivalent to sum over k of small ck star capital CK, and that is equal to sum over L of small dl star capital DL. So that essentially is one of the Parseval identities. So over here, if we set small a ket equals to capital A ket, so that leads us to norm of psi given by square root of sum over k mod ck square, and that is equivalent to root over of sum over L mod dl square. So that implies that these coefficients are such that if you sum over all these all the squares or modulo squares of these coefficients, that is going to be identical irrespective of which basis set you had used. And like this again has an interesting connection to quantum mechanics when we are talking about conservation of probabilities. The object has to exist in one of the states eventually, and the sum over probabilities of its existence in various states is supposed to be independent of the basis used. The next result which follows from here is or rather the next result which is relevant is Kochschwarz inequality. So where what we talk of is on the same lines as the typical vector identities that we had for conventional Cartesian coordinate vectors. The dot product of A dot B had a magnitude which was less than equal to the product of magnitudes of vector A and vector B respectively. So this was the case because in the case of Cartesian vectors, we knew that if there is a vector B and a vector A and there is an angle theta, this A dot B is going to be mod A mod B cos theta, and cos theta is going to be bounded between -1 and 1. So in magnitude wise, it is going to lie between 0 and 1. Therefore, like this result is trivial to see that it's primarily a consequence that cos theta is bounded between 0 and 1. So now in the case of general ket vector psi and phi, the Kochschwarz inequality reads as follows, where we are looking at this inner product of phi and psi, and when we look at its magnitude, that should be less than equal to the product of norms of phi and psi. So this has a fairly elegant and short proof. So let's construct a ket vector phi plus a psi, where a is a complex number, and take inner product of phi plus a psi with itself, and that is greater than 0 as it is square of a norm. So this can be 0 if and only if phi plus a psi is a null vector. Okay, so that means that phi is going to be minus of a psi, and that essentially implies that phi and psi are linearly dependent. So thus, this inner product of phi plus a psi is going to read as the inner product of phi with phi plus a star inner product of psi with phi plus a inner product of phi with psi plus mod a square inner product of psi with psi itself, and that is greater than equal to 0 for all a contained in complex numbers. And this is because of the fact that a and psi are not linearly dependent. So therefore this result has to be positive definite. The quantity on the left hand side has to be positive definite, or 0. 0 is also allowed. Okay, so it cannot be no. 0 is allowed. Yeah, 0 is allowed when it is linearly dependent, and it is greater than 0 when that is not the case. So in general, a is going to be written as minus of dot product of psi and phi divided by the norm of psi, and a star is written as dot product of phi with psi divided by norm of psi. So that implies that the quantity on the left hand side, which is inner product of phi plus a psi with itself, is going to be equal to a product of norms of phi's and psi's minus the inner product of phi and psi mod square, and this is going to be greater than equal to 0. So that leads us to this interesting result, which is that the dot product of two kets modulo square is going to be less than equal to the product of norms of those two vectors. Similarly, for addition, there is a follow-up rule which is relevant, and in that case, for two kets psi and phi contained in the linear vector space, the norm of the added vector, that is phi plus psi norm, is always going to be less than equal to the sum of norms of phi and psi, and this is the famous triangle inequality. So these results are going to be useful as we proceed further. So I will close this video right now. Thank you.